Okay, this is one small dot point, but it is big. Okay, we need to analyze the operation of DC generators, AC generators, and a special type of motor called the AC induction motor. And this one is not a simple motor, unlike the last video on a simple DC motor. But speaking of which, you might remember the simple DC motor looked something like this. It had a split ring commutator connected to coils, and that's the rotating part. And then it had brushes connected to a power supply, plus the magnets, and all the bits in red here are the stationary parts, the stator. Okay, now this is really cool, right? Because this device here converts electrical energy from the power supply into mechanical energy or kinetic energy as the coil rotates. But it works in reverse. If you put in mechanical energy into the coil, electrical energy comes out. So what we need to do is we need to replace the power supply with something to use the electrical energy. So let's say a light bulb, because that's just the classic. Light bulb, you can see the electricity, so that's why I like using light bulb. And you need some way to input mechanical energy. So onto the end of this, you could attach like a little fan, windmill sort of thing. And so when the wind blows at it, wind blows towards it, it spins the coil. The spinning coil activates Lenz's law because you have a changing flux through that coil. That's going to generate a current that generates your electricity. Okay, and this, just like this was a simple DC motor, when you run a DC motor in reverse, you get a DC generator. Man, that took me a long time to write. Okay, running out of time. So AC generator is actually not that much more complex, which is nice. The only difference, or the biggest difference, is in that commutator. Instead of a split ring like this, you have whole rings and two of them. One for one side of the wire and one for the other, or one for the input, one for the output. I don't know what you want to call it. So very similar design, except we have two rings. So we have one ring here and one ring here. This ring, I'm going to miss that second one on purpose, is connected to one side of the coil. So here's our coil, and the other side of the coil is connected to that ring. Okay, both rings are then connected to their own brushes. So this brush here, and they're both connected to whatever's using the electricity. Again, let's say it's a light bulb. And you need your magnets, of course, north and south. Oh, and some way to turn it. Let's say this time we have a handle of some kind and you're turning it by hand. There you go. You're winding it, spinning it round and round. Okay, so in this case, this wire here is always connected to this side, to the right side of the light bulb. So when it's coming up through here, it's going to make current in a certain direction. When it's coming down through the other side, so after it's made half a turn, the current's going to flip over. So this is going to produce AC electricity. Okay, instead of writing DC generation, draw a straight line for DC, boom, AC squiggly line. Excellent. Now, in reality, because this coil, it's going to be producing the most current when it's horizontal, and it's not going to be producing much current when it's vertical, you actually get fluctuations. So even though the current is always in the same direction, it kind of fluctuates, goes up, then down, then up, then down, then up, then down. So this is really more of what that would look like, whereas the AC also goes up and down, but it actually goes below, changes direction. So it actually goes above and below the line, whereas this one stays on top. Okay, that wasn't so hard, was it? This is how we produce electricity in the vast majority of cases. Solar panels don't work this way, but coal power, nuclear power, wind power, hydroelectric, they all use one of these generators. In fact, they almost all use the AC generator, and this is the type of electricity that gets sent around to our homes. And that's because it's AC, That means if you put it into a solenoid, it creates a changing magnetic flux through that solenoid, and that changing magnetic flux can be used in a transformer. And as we looked, and as I showed in the last video, the video before, transformers can save power. With great power comes great current squared times responsibility, no times resistance. And that means that by transforming it, we can reduce the amount of heat loss due to resistance. Okay, now the thing I've been dreading, the AC induction motor. AC induction motor requires AC voltage. And as I said before, AC voltage does this strange thing, whereas if you put it through a solenoid, you get a changing magnetic field. So AC induction motors are also called three-phase, or some of them are three-phase AC induction motors, and that means you've got three different pairs of solenoids, each attached to their own AC power supply. Okay, I'm going to try and draw that. We've got this pair of coils here, boom, boom, and they're going to be connected to their own power supply. But I'm not going to draw the wiring because that's going to get really confusing. Instead, I'm just going to have a graph down here, and in green, I'm going to show the power, the AC electricity going into the green coils. Okay, and so I said there's going to be three pairs of coils. So we're going to have a red one here, here. Oh, that was terrible. And let me see. How can I do this? Boom, boom. Yeah, okay. I'm practiced at drawing this. Don't try this at home. Okay, good. That was, yeah, it's good enough. And let's have a blue coil here to finish off the pairs. This one's coming in like this. They're meant to form a circle, kind of like a weird cult or something. And this one is, that started there, this started there, this one's going to start here. Oh, look at that. Beautiful. Okay. Three-phase AC induction motor because they've got your AC electricity in three phases, green, red, blue, and that corresponds to these coils around here. So let's analyze what happens in these coils. What's going to happen? There's going to be induction, so there's going to be change in flux, creating a current somewhere. Let's look at that change in flux first. So we can see that these green coils here, let's keep it in green. As the current through them rises in this direction, let's say that rises so that this becomes north and this becomes south, okay? So it's going to rise, making those poles stronger, and it's going to make them weaker again. And while this is becoming strongly north, let's see what's happening to blue. Blue is becoming strongly south. Blue is becoming strongly south. Okay, now, nope, you know what? Forget about that part. Green's becoming strongly north. Now, as the green loses its north, loses strength in that north pole, red is gaining strength in the north pole. Essentially, it's as if the north pole is moving to this red coil here. Okay, so as green dips, red rises. So the north moves across there, the south moves across here. Okay, and then we see as the red dips down, the blue rises. So when the red loses strength in its north, and this south loses strength in its south, they move across to here. Then as the south, as the north moves across to there. Yeah, I'm not sure if I've drawn this entirely right. Sorry, I stuffed up a bit here. That's not supposed to be a north, it's meant to be a south. And you can see that this magnetic field is essentially rotating around, right? It's going around in a circle. And so the field lines are going around a circle. So the field lines go from north to south. You can imagine this arrow is rotating around like this as time goes on here. So what does this do? There is an object inside here making use of this changing magnetic field. Okay, we can sort of imagine it like a, let's imagine it's a cylinder, right? Coming out towards us, but I haven't drawn it very well. This North Pole here, as it increases in strength, it increases the amount of magnetic field lines going into the surface of the cylinder here. That surface is going to respond. It's going to try and oppose the change in flux. It's going to produce its own flux against the north, creating its own eddy currents going around in this direction. So it's going to produce little eddy currents going around like this on the surface up there. Then as that north dies down, right? As that north dies down and this north increases in strength, this position here, sensing the disappearing north, is going to create its own magnetic fields in the same direction as this north was producing. It's going to try and bring them back. So now it's going to be producing magnetic flux in the other direction, and it's going to have its own little south pole up here. Remember, this south pole is appearing as this north here is disappearing, and this one is appearing now. Stay with me. This is the important part. The south pole is now attracted to the second north pole in the red. Okay, so this starts to spin. South's attracted to the north there. What happens when this north here starts to disappear? At this point down here, that north disappears, this north appears, the south now follows that north pole, and etc. So it's going to spin to follow the spinning magnetic field. How fast it spins depends on how quickly these go up and down. And remember, for normal usage in Australia, this stuff moves at about 50 hertz. So it goes up and down at 50 hertz. That's going to dictate the speed at which your motor spins. Now, this is, a complicated setup. You need 3 different sources of electricity to create this motor. Why do we do it? For a start, there's no brushes, no commutator. These contact points here, if we're pretending that this was a motor, because as I said before, it's about the same design. These contact points here, they rub against each other constantly. They wear out. It's a source of sparking. It creates ozone, that kind of thing. Wearing out over time is no good. Over here, all the energy is transferred via induction. There's no touching parts. It needs an axle in the middle, and that axle can be attached to anything. You can grease it up real good. It doesn't need, you try and minimize friction as much as possible. So no wearing out, no parts that wear out. It also happens to be a very strong motor, very reliable. Changing the speed of it can be quite difficult, but it works. It's a powerful motor. Hence why it's one of the most common motors you'll find used around the world, especially in big industrial processes and in Tesla cars, because it was Tesla himself who invented this motor. All right, happy physicsing.